cloud. Okay. Today, main outline. Let me check again whether. Okay. Finish shared. So today, outline of today's class, like discussion, is quantile regression. Quantile regression. I'm going to derive those things mathematically and give you an example and rationale why we need quantile regressions. Okay. And this is the 6th week. Okay. And then 7th week, we will discuss. 7th week, we will discuss linear mixed effect model or mixed effect model. Mixed effect model. And 8th week, midterm exam. Clear, right? 8th week, midterm exam. Midterm exam on what? The data analysis, data mining part. Okay. That 84 problems and functions, all of these things you have done, and 40 problems you have done. From there, I might give you maybe 12 to 15 questions. And remaining 15, 20 questions is coming from Poisson regression, negative binomial regression, lasso, Rees, elastic net, quantile regression, and linear mixed effect model. Those are technical questions. All questions are coming. Clear, right? Clear, right? So there will be exam on the 8th week. Today's class is the 7th week, the 6th week, and next week will be the 7th week. 7th week, I'm going to discuss linear mixed effect model that I mentioned in here. I see 2% in the online, and 8th week will be the week which is, I guess, 12. Okay, I guess 12. So Vaishnav, viewer in the online, please make your arrangement to come to the class. Okay.
Yes, Professor.
Clear, right? Okay.
You mentioned the data mining part. You said you will get questions.
Yeah, like 15 question is coming from there, 15 to 20 questions.
Because remember the first week, kind of do a separate task. People who have taken the class previously.
Each question will be customized question. Okay. Each question will be customized questions. You will see it by leaving one seat blank. During the exam period, no use of the email, and I will see it in the back. No uses of the email, no uses of the WhatsApp. Understand? Phone must be switched off. Okay? All question is coming technical questions. If you do the homework, you do good in the homework, so that means you are understanding. So I am asking you technical questions from those maybe 15 or 16 or 20 questions is coming from data analysis, data mining, how the code, different kinds of data you will get. The data that you will get is different from the data she will get. Okay. So it will take almost 6 to 8 hours for me to write the question, customized question. And then remaining things is asking you different types of modeling questions. This is the scenario, what type of model you are going to use. Clear, right? You will write 1 or 2 sentences. Okay. So after that, let me discuss little bit about Rees regression that you have done. What is Rees? Rees regression, lasso, and elastic net. Maybe next 10-15 minutes I'm going to discuss it, so that you already watched the video, right? The video that I have uploaded, right? So take a look at that. This is the regression model that we are going to use. We know, all of us know about this regression model. Clear? This is the regression model developed by the Galton 1805. 1805, this regression model is developed. y equal to x beta plus epsilon. Okay. So y is our response variable. X is our predictor or independent or explanatory variable. Beta is the regression parameter, which is known as the partial regression coefficients, because they can explain partially. Okay. They can explain partially. What does that mean? They can explain partially. So yi equal to 5 plus 3x1 plus 4x2. So this is the model. So how can I explain these things? Why you use a partial regression model? 1 unit change in x1 on an average 3 unit increase in y, keeping other variable fixed. So partially you can explain. Okay. There is no way that you can explain it simultaneously. 1 unit increase in x1 and x2 on an average 3 plus 4, 7 unit increase. You cannot say that. Even though this is multiple linear regression model, the regression coefficients are called the partial regression coefficients. You will obtain it by partially differentiating with respect to each parameter. Clear, right? Are you understanding? So your exam question will be technical questions. Why it is called partial regression coefficient? So that is the answer. Okay. So what is the limitation of this regression model? Suppose there is a number of parameters or covariates that are in here, beta 0 plus beta 1 x 1i, beta 2 x 2i, beta 3 x 3i plus beta 4 x 4i. It will go like this way: beta k, beta k I, beta 4, beta k x ki plus epsilon I. This is a multiple linear regression model. Okay, this is a multiple linear regression model. Online people, you can see my document, right? Where I am writing. Eric and Vaishnavi, you can see the document, right?
Yes, Professor. I can see it.
I cannot hear you. What happened?
Yes,
For some reason,
Professor, I
Eric,
can see it.
could you speak, Eric?
Yes, I can see it too.
Oh, what happened? Sometimes they got disconnected. So many things. We should know all of these things. Why there is no sound? I cannot hear you. So if you ask me question, in that case, I may not hear. Let me check in here. Paste speaker and microphone, echo cancelling speaker. Switch to phone audio, leave computer audio. Okay, I don't know what happened, but if you listen to me, that's fine. Now take a look. What is the problem of this model that was proposed by Galton in almost 220 years ago? The problem is, if you in the class, I ask you, request you, advise you not to speak. Okay, that will take my attention what I am teaching, please. So take a look. What is the problem or limitations of this model? The limitation of this model is if xi's are correlated. So that means this one and that one has a high correlation. X3i is a height, X4i is a weight. In such a cases, this estimate will have a high value. This is called inflation, inflated value. Understand? So that is the multicollinearity problem. If xi's are correlated, then there is a multicollinearity problem. Then there is a multicollinearity problem. So what is the multicollinearity problem? Independent variables are correlated. In such a cases, if I still use this estimate, beta hat x prime x inverse x prime y, if these estimates, if I'm going to use, these estimates will be inflated. In such a cases, prediction will be very unstable. Understand? So in order to solve this problem, in 1970, almost 175 years later, after Galton proposed this, the two statisticians, their name is Orell and Kennard. They proposed regression. They proposed regression. 1970, these two statisticians, Orell and Kennard, they proposed regression. So what they have done these things. Yi equal to x beta plus lambda, then sum of beta I square, I goes 1 to suppose P. This penalty they have used, they made restrictions that we have to make this beta I, sum of this beta I must not exceed certain threshold value, and then Lagrange multiplier, all of those things they derive, which I already uploaded in the D12, the complete derivations, right? So this is called the regressions. They added a penalty which is known as the circular penalty for 2 dimension, because this is the equation of a circle. So if you want to know x square plus y square equal to 1, this is the equation of a circle with a radius equal to 1. So if you take a look at that, this is beta 1 square plus beta 2 square, if it is a 2-dimensional. That is what they call the regression. In order to do what? In order to reduce multicollinearity. And then in 1996, Tipshirani, very famous Tipshirani, Robert Tipshirani in Stanford University, very famous statistician, top known. He said that this problem, this penalty, they can shrink it. Inflation by multicollinearity shrink by this penalty. They said that, but some of the variables in the model should be zero, has zero influence. And then he give a lasso model. He give a lasso model by adding this x beta plus x beta plus lambda, sum of I goes 1 to k, and then they put here beta I. He put there. They put a penalty here. In that penalty, this is the equation of a diamond. This is the equation of a diamond in 2-dimensional case. If you watch my video in the video that I have uploaded, I give an explanation. In 2 dimension, it is a diamond. So in such a cases, you have a figure like this. You have a figure like this. And this is the point of discontinuity. This is the point of discontinuity. If this is your parameter space, and certain states, they will come and become 0. Because when this touches in here, this is beta 1, this is beta 2. Beta 2 is 0, beta 2 value is non-zero in here, but beta 1 value is 0 in here. Similarly, beta 2's value is 0 here, non-zero in here. So in such cases, when it touches, it become 0. So the figure, the lasso figure that said that, but in this case, when it is a circular penalty, it shrinks, but it cannot make the 0. So that is why they previously, this is called the shrinkage estimator. Shrinkage estimator, and this is called the sparse penalty or sparse. Sparse means what? Some of the variables, some of the xi's are non-zero, and rest must be 0. That means has no effect on the response variable, must be 0. Rest of the variable must be 0, and then they name it as a sparse or sparsity. You understand, right? So sparsity means what? Suppose you want to run a model. You have a dependent variable y, and you have a 50 independent variable, and you do not know which one to give in the model. What you know? Well, we know the lasso put all 50, unnecessary variable will be kicked out, unnecessary variable will be made 0. That will be done by the lasso, and famous Tipshirani did these things. Very famous. After giving these things, it is almost 200 years later, after regression was proposed in 1805 by Galton, it take almost 200 years to come up with this. His contribution just of this little thing, but it has a huge application. When you do the bioinformatics things, genetics things, variables after variables, you do not know which one to put, which one not to put. Understand? Before giving this model, before 1970 and 1966, for running this model, I am talking very important thing for you. Before 1970 or 1995, how did a statistician handle those variable x1i, beta 2 x2i, beta 3 x3i, and then goes up to beta k xki plus epsilon I. Some of you might ask me question, hey professor, it is just the 20 years and even not 30 years old, lasso was proposed, and this regression was for the shrinkage estimates. So that means estimates become inflated because of the multicollinearity among explanatory variable that is reduced by the Rees regressions. And then before 1970 or 1996, how can statistician scientists handle all of these variables? Do you understand? So during that time, there was another procedure known as forward selection. Forward selection. Nowadays, university does not teach these things, selections. Backward selection. I'm going to tell you verbally what is that. Backward selection, stepwise method, and stage-wise method. Stage-wise method. What does that mean? Forward selection means they put one variable and then the two second variable, all combination of the second variable, all combination of the third variable, all combination of the fourth variable, and then each time they enter, they compute R square value, adjusted R square value, and in that way they will select the model. Still old SPSS things, those things still existing, forward selection, backward selection. And backward means you started all of this model variable and then you take out one and then again take out one and then give it back and again take out one. This is the way called the backward selections. Stepwise means it at one steps you will try with all of these, like 5 variables, and then next one we will try 7 variables stepwise, and stage-wise something like that. So stage by stage they will go. So before the discovery of lasso and these regressions, people use backward selection, forward selection, stepwise and stage-wise. Nowadays, in the university regression syllabus, they no longer teach these things. Maybe taught, but no longer that much. We studied this stepwise, stage-wise, forward selection and backward selection when we are a third year undergraduate students. We learn these things. I'm talking about like around late 1999. Lasso was discovered, but the book was not updated. Our professor did not have knowledge. We come to know lasso after coming to the USA. You are understanding, right? I'm speaking, but giving you the background. Okay, what is elastic net? Elastic net. Lasso has a little problem. What is the problem? Suppose you have a n and you have a k. Okay, k equal to number of variable and n equal to number of observations. Okay, so usually high dimension data means what? High dimension means k is bigger than n. Understand? Number of variables is bigger than the number of observations. That is called the high dimension data. Okay, write down what is high dimension data. High dimension. What is high dimensional data? Okay. K greater equal to n, that means number of variable is bigger than the number of observations, then the data is called the high dimensional data. In such a cases, if you use the lasso can kick out non-important, unimportant variable, and then it can stop up until k. After k, suppose we have here 100 observations, but we have variable in here, suppose 200 variable. Lasso can kick out up until 100, and after that he cannot kick out, even there is something is in there. Understand? 100 observations, 100 rows, 200 column, 200 variable. Lasso cannot kick out more than 100. Lasso can kick out up until 100. Even though there are few more unimportant variable, lasso cannot kick out. In that case, though Tipshirani developed lasso, but it take another 10 years by another Stanford professor. His name is Trevor Hasty. He said, I will add the penalty from lasso and Rees. So he add the penalty from lasso and Rees, and then he said that it is elastic net. So they can, and rest of the parameter can be shrink. Understand? So that's the history. Okay, but all of these, Rees regression, lasso regression, Rees, lasso, elastic net, all of these estimates of betas are biased. But even though they are biased, in my opinion, unbiasedness concept is not, it is a property of estimator, but in some cases, there is a variance, there is a trade-off between bias and variances. In some cases, unbiasedness is not as important as the reducing of the variances. Understand? Unbiasedness you found, but the variances is very high, unstable, and prediction will be very unstable. In that case, the bias estimator would be better. And then Rees regression, lasso regression, and elastic net, all of them are bias estimates. So that's the thing. So 8th week, there will be in-class exam. There will be questions from all the materials that I have covered. So you need to prepare accordingly. Okay, let me start with the quantile regression. Yes.
So doesn't that elastic net now takes care of Lasso's limitation?
So it is taking care some of those things. So for example, if you have a x1, x2, x3, suppose x50, okay, x50. So they kicked out, suppose from the 50, they kicked out, suppose 30. 30 is kicked out, that is sparsity, they known as rest of the variable sparsity. And then how many variables remaining? X1, X2, the new variables are 20, right? So what the elastic net do, rest of the variables, their estimates will be shrinkage estimates. That is why they are adding these two penalty together. You are talking about, so this is the multiple regression coefficient estimates. And this is, if I take the expected value of beta hat, it come up with that thing. Okay. But if you take the expected value of beta hat, this is just the regression. This is called Rees regression. It is not equal to beta. If you take the lasso, regression is not equal to beta. If you take elastic net, regression is not equal to beta. Why? Because additional penalty I am adding in here. Additional penalty, additional penalty, additional penalty. Why I am doing that? In order to reduce extreme variability in the parameter. So if there two variables are correlated, what will happen? The estimates of beta will inflate it, high value. In such a cases, with this high value of the estimates, if you make a prediction, prediction will be unstable. So in order to handle those problems, they are doing variance and bias trade-off. This is called. So estimate is biased, but variability will be reduced. Yeah.
So what happens?
So no multicollinearity, multiple linear regression you are going to use. Now no multicollinearity, lot of independent variables. Then what you are going to do? You are going to sparsity. Sparsity means some of the variables are not important. You have to use lasso. Okay, and then if you see lot of variables as well as multicollinearity, then you can use elastic net. Okay. Okay, let me start quantile regression now. Okay. Quantile regression. First of all, we need to understand what is quantile regression. If we have a data, from that data, if we arrange them minimum, and then that is a maximum by ascending order, if I arrange them, right? I have a data, if I arrange them minimum to maximum, and this is called the Q1, this is called the Q2, and this is called the Q3. This is called the first quartile, that is called the second quartile, this is called the third quartile. So this is called the first quartile, Q2 is the second quartile, this is the third quartile, right? So quartile divides the entire data in 4 equal parts. So this is bottom 25%, okay? And this is between 25% and 50%. This is between 50% and 75%. This is called the top 25%. This is called the top 25%. Or this is called the bottom 75%. Or this is called the bottom 50%. Or this is called the top 75%. If top 75%, if you consider, it is like this. Okay. So top means from there to top, you will get the 75%. So these are called the 25th percentile also. First quartile, 25th percentile. This is called the 50th percentile. This is called the 75th percentile. Okay. Now, how to compute these quartiles? These percentiles together is called the quartiles. How to compute the quartiles for discrete and continuous case? That is what now I am going to discuss. After that, I am going to derive quantile regressions and how the quantile regression solutions are obtained by using different methods. That is what I am going to discuss. And then I will go to show you real life example. Those are the things I am going to discuss now. So the real life problem I am going to discuss later, like how to use linear programming approach to compute, to estimate the parameter in the regression model. Where is my material? Okay, here is my material. Clear, right? Any question? Okay. Let me tell you a little bit history. In 1975 and 1977, famous statistician 2K He was a professor of Ohio State University. In 1975, he gave a speech in the gatherings of lot of top statisticians. Okay, his speech was that the regressions that we are using, it always take a look at the average. That means 50%. Okay, it always look at the average. That means 50%. If this is the data, it always look at the average regressions. So then he said in his speech that we should try to develop a regression which can predict other percentile distributions of the response variable. So we want to take a look at the top 5%, like bottom 5%, something like that. If this is the data, this is what his speech. And after that speech, very famous 2K. In 1977, Quantile, I think University of Illinois, Urbana-Champaign, or maybe University of Illinois, Chicago. I don't think it is University of Chicago. His name is Quantile. His name is Quantile, and Roger, another guy. I guess I have a paper on quantile equations where I use quantile equations. Sorry for the misspelling, but is the name. They come up with the quantile equations, and then their paper got published in the econometrics journal, and then this became a very famous. Okay, so now let me discuss how to compute quantiles. So suppose we have values like this. Suppose we have values like this. I arrange them in ascending order: 3, 4, 7, 9, 10, 11, 17, 21. Okay. So this is the values. I want to find theta equal to 0.60. That means 68th percentile value. 68th percentile value. How can I find that? This is the 68th percentile value that we want to find from this data. Okay. So let us try this way. It is arranged in ascending order purposely. If I give you data and ask you find the 77th percentile, that is the way you have to find these things. So how can you find that? Probability of x less than 10. X less than 10, what? 4 over 1, 2, 3, 4, 5, 6, 8, right? Which equal to 0.5. 0.5 less equal to 0.60, right? Clear, right? What do we want to find? We want to find a 68th percentile value, right? From this data, what is the 68th percentile value? I randomly pick 10, x less than 10, x less than 10, how many? 1, 2, 3, 4. So 4 out of how many? 8. 4 over 8 equal to 0.5. Okay. 4 over 8 equal to 0.5. Okay. So then this 0.5 is less than 0.60. So now, is this that means is 10 is less than 10. So what will be the 98th percentile? Let us check another one. Suppose I want to do probability of less equal to 10. Less equal to 10 means 5 over 8. 5 over 8 equal to what? 0.62. Understand? Now I say less equal to 10, right? Less equal to 10. So now 0.62. It is big, 0.62 is bigger than 0.60, right? So what is the 68th percentile now? Between there is no number. Between 9 and 10, there is no number.
Yeah.
I have given you this number and asked you find 68th percentile. So 9 is the 68th percentile, right? Agree or not? Are you okay? Are you okay? Samita, are you okay? I have to find that is coming purely from the probability. That is purely coming from the probability. That's the reason I did not write this equation at the very beginning. Let me write now equations. Percentile value is computed if x is a variable. This is the percentile value xi and theta, which is in this case, this xi theta is exactly equal to 10 or less than 10. So this is my percentile value I am putting in there. That should be equal to point theta. Sorry, not point theta, just theta. Just theta, where theta lies between 0 and 1. So this is the definition of percentile. This is the definition of percentile. So theta equal to what? Theta equal to, so percentiles means 0 to 1. Okay. You are not clear yet? You want me to explain it again? Okay. So let me explain these things to you. I can give you a data. I can give you a data and ask you find 71 percentile. If I give you the data, ask you find 71 percentile, your first responsibility is to arrange the data. Is to arrange the data from smallest to largest. Okay. And then randomly pick a number and then try to compute below that number how many numbers lies, which will be in the numerator and total number in the denominator, and compute the probability. So it is not. So for example, if I want to find the 71 percentile, let me check. If I put P less equal to X less equal to 11, then 6 over 8, right? 6 over 8 equal to what? Someone of you help me. 6 over 8 equal to what? 3 over 4, 75%, right? Right? So if 75% is 11 my 71 percentile value? Is 11 my 71 percentile value? No. No, right? Because probability exceeding 71. Clear now? This is the way, if your variable is discrete, you can find. Now, you can also find it is in terms of the probability. Distribution. You remember there are two types of distributions, right? Two types of probability distribution. One is for discrete, another one for continuous, right? Right? One is for probability, another is for continuous, right? Now, for the discrete one, suppose I have x equal to x, okay? Then I have 10 choose x half to the power x, not half, put here 1 over 3 to the power x, 1 minus 1 over 3 to the power 10 minus x. This is the distribution. And x takes value what? 0, 1, 2, up until 10. Right? Binomial distribution. If I give you this distribution and then I ask you, find the 75th percentile value. Find the 81 percentile value. Are you understanding? Find the 81 percentile value. If I ask you find the 81 percentile value, you have to find this probability. 81 percentile value, then what you did? You did like this. Probability of x less equal to, suppose you put here up to 10, right? You put here suppose 7. You put here 7. Are you understanding? Are you understanding? Okay. So that means 7 means what you are computing? Probability of x equal to 0 plus x equal to 1 plus up until probability of x equal to 7, right? So I have to compute these things. Now we have a machine. Previously, there was a binomial table. People use binomial table. Okay. So R is called D. D binom, P binom. P binom P by norm, and there is a 7 out of 10. Probability of success is 1/3. Check. Okay. So probability of success is 1/3. Let me check if did I write it correctly or not. Let me see. 10, 7, 1. Oh, what I wrote is fine. It should be 7. It should be 10. I'm getting 99. P binom. P binom. Let's check. P binom means Q size. Oh no, it's not P binom. Maybe Q quantile. Density distributions. Okay, that is the distribution function, quantile function, random rate generation. Yeah, that's right. So that is the distribution function from 7 to all the way to the left. Okay, D binom is the density. It is a particular probability. P binom is the cumulative. Q binom is the inverse one. R binom is the this. Yeah, it's right. Whatever I said. So then what is it? Is it a 7 is a 81 percentile or not? Is 7 81 percentile or not? Not, right? Because it's going to 99. So now, if you go put here, suppose 4, I'm getting 77, 78. Is it 81 percentile? I have to check another one. Okay? I have to check another one. Let me put here 4, 5. Yeah. So that means 4 is the 81 percentile. Are you understanding? This is the way you have to compute percentile from the discrete data and discrete distribution. Now, how can you compute it from the continuous distributions? Let me show this. Then I will go for quantile regression derivation. Now, suppose all of you already know about these things. Do you know about these things? What is this? What is this? It has a name. It is a name. Normal distribution? What? Exponential? What did you say? No, this is called the exponential distribution. Exponential I showed you how to compute quantile value from discrete data as well as discrete binomial distributions. Now, how can I compute quantiles from this distribution? Okay, so take a look at that. Suppose I want to compute here 83rd percentile value. Percentile value. This is what I want to compute. So how can I compute that this is continuous? So continuous. So I have to compute 83rd. Are you saying point? It is called the xi, Greek letter, 0.83, integrating from 0 to that quantity. This is what target we want to find. Why I am integrating? Because this is continuous. Because this is continuous. Because this is continuous, okay? So now I have to put here lambda e to the power minus lambda x dx. equal to 0.83. Equal to 0.83. Now we have to solve this. How can you solve this? 0.83 lambda e to the power minus lambda x divided by minus lambda, and each goes 0.8320. 0.8320. Now solve it. 83. This and that cancelled out. There is a minus e to the power lambda x. 83 and 0. 0.83. If I plug this one, it will be negative e to the power minus lambda xi 83 minus 1. So from there, now we want to compute here e to the power minus lambda xi 83 equal to 0.17. I want to find, if I take the log, then we get lambda xi 83 equal to log of 0.17, and then xi 83 equal to what? Log of 0.17 divided by negative lambda. Now suppose lambda equal to 5. If I plug lambda equal to 5, which is an unknown parameter, needs to be estimated from the maximum likelihood method. If this is the scenario, then xi 83 equal to log of 0.17 divided by negative 0.5, and you will get a result in here. That's the way any quantiles of data or distributions are derived. So you understand what is quantiles, right? Quantiles means in your entire data is 100%, and 100% I am interested to take a look at a certain quantiles value. So it is also known as the percentile. You are taking, quantile is a general one, but specifically you can say it is a percentile. And sometimes entire data is divided into 10 equal parts, known as the decile, quartile, decile, percentile, something like this. Okay, let me start with the quantile regression derivation now. So derivation of the quantile regression start. Let me give you first the example. Before giving you mathematical derivations, let me first give you the what is linear programming. If I'll give you the linear programming then. So take a look. This is y1. So you write like this. Y1 equal to beta 0 plus beta 1 x1. And then you write y2 equal to beta 0 plus beta 2 x2. Right? Then y3 equal to beta 0 plus beta 2 x3 on the different values. So you can write here yn equal to beta 0 plus beta 2 plus xn. This is the way equations are written, right? Right? This is the way equations are written. So I want to construct. So if I say like my quantile equal to 0.50, so that means I am taking a look at the median average, right? On the other hand, if I say that no, my quantile equal to 0.75, so that means 25% is in the above, 75% is in the below, right? So that means I am splitting them in the two parts. I'm splitting them in the two parts if I say these things. Okay, so on the basis of that, if I write a function to solve, g is the function, suppose that has twice x plus 5y, twice x plus 5y, g is the function where x and y are unknown, and we need to solve this or minimize or maximize this with the constraint, what are the constraint? Constraint is x plus 4y less equal to 24 and 3x plus y less equal to 21 and x plus y less equal to 9, where x greater equal to 0 and y greater equal to 0. So we want to maximize this function, that whatever will be the value of x and y, if we plug in, it must not cross 24. These are the conditions. Okay, I cannot, if I put here x equal to 100, we have to put here a number so that 100 plus this number would be less than 24. That is the condition. I cannot exceed those things. Are you understanding? So these are the conditions. So when like Amazon and other people run their big businesses, they need lot of engineers. They optimize their algorithm and model. How can they do optimize this way? So the Amazon driver, when he comes out in the morning, his location was calculated by the remote engineer or artificial intelligence. Well, the first way you will go there, and then you will go there, and then way this, that. So those of the algorithm is run in his machines. Okay. Ultimately, what they want to minimize their cost function. They want to minimize their cost function, or sometimes they want to minimize their time. Time is their constant. You have to finish all of these words by that many. So what algorithm runs? This is the algorithm. It is known as the linear programming. We have to find x and y by using this information so that this restriction is satisfied and also these functions get maximized or minimized. Do you understand? Do you understand? So under these conditions, x and y you have to find that satisfy these, and then you have plug this x and y so that it will be maximized. This is called the linear programming developed in Stanford University. Whenever I read something, I read their history. Okay? A professor in early days, he came to the class and he is teaching in the graduate class some of these things. And one graduate students came very late in the class. And then professor at the end of the class write an equation like this. Then professor said, if I can solve this problem, then I will be famous. I do not know how to solve this problem. So the graduate students was thinking about this. The graduate student who came last, because during that time, lot of boards, Stanford University. So graduate students who came late in the class, he write down the problem. He said that this is a homework. Okay. And the next class he came, he handed the homework solutions. So this is the professor said that no, this is not the homework. Did you solve it? Yes, professor. Here is the solution. You understand? So the student went home, he think that how can I solve this problem? How can I solve this problem? And he solved this. And that's the beginning of the linear programming or optimizations program. So now, as it is a simple one, in our cases, listen, in our cases, sum of this equation is greater than 75%, sum of these values greater than 75%, sum of these are less than 75%, right? Because we are fitting a line corresponding to 75%, right? So this is the restrictions, that is x1 like beta 0 plus beta 1 5 beta 0 plus beta 3 5 x and y's values are given and these restrictions are given, then we have to minimize this from there. Now take a look what I am doing in here. Based on these equations, we need to construct some graphs. So the graphs I have to construct here. So one graph I want to construct here from all the way here to there. The point is in here 0, 21. I'm going to explain these things. Let me write it first. And this is the equation 3x plus y equal to 21. 3x plus y equal to 21. In this case, if you plug x equal to 0, x equal to 0, x equal to 0, then y equal to, you are getting 21. So that is what the 0 and 21. And this one, if you plug y equal to 0, then x equal to, you get 7. Here you will get 7, 0. You got it, right? Did you get this 7, 0? 3x plus y equations, if I plug on that line x equal to 0, then y equal to 21. If I plug y equal to 0, then I get x equal to 7. So this is one equation. Then another equation, I am starting from 8. I am starting from 9. So if this is 21, then that is 10, this is 9. So let me start in 9, and then it should be another one is 24. So that should be, if x equal to 0, y equal to 9, if y equal to 0, x equal to 9. Okay. So now 7, 8, 9, let me put like this way. So in this case, 9, 0, and in this case, it is 0, 9. And then equation is x plus y equal to 9. Clear, right? And then finally another one, 24 one, if I plug 24 one, if I plug x equal to 0, y equal to 6. X equal to y equal to 6. And then if I plug y equal to 0, x equal to 24. 9. So that means it will be 24. So I can write here 24, 0 in here. And then if I plug that one 6, 9 is 5, this is 6. So I can write this equation like this. Okay. So this is equal to 6, 0, 6. 0, 6. Now, all the solution is less than. Are you seeing all less than, right? Less than, right? All of these are less than, right? So less than means this is a feasible area, acceptable area. Are you understanding? Feasible area. So that means this is the points, this, and that. So here x equal to 0, 0, here 7, 0, here 6, 0, 6, and that is the point which is that is the point. Here we got, okay. So we got actually 1, 2, 3, 4. My figure got cut off. Yeah, that should be, it should go upward. Okay, I will upload these things. That is a figure need to be constructed very carefully. There should be another point because of the way I draw the figure does not look good. So I will upload these and then I will explain these things from the figure. So now take a look at that. Here I have corner points. I should be careful about writing this. Twice x plus 5y, right? So corner points, and here we have 0, 0. We have, this is my origin. This is a 1 point, 7, 0. This is the point, second point, 6, 3. This is another point, 4, 5. And that is another point D equal to 0, 6. When I upload this graph, you will understand when I draw these things, drawing become little mess. So if you take a look at these solutions that I'm going to upload, your confusions will be gone. But now I will get a region that will have altogether 5 points. Okay, that will have altogether the way this graph is drawn. This is not the correct way drawn, because the graph needs to be drawn in a graph paper. You understand, right? Graph needs to be drawn in a graph paper in order to match actual scale. So I should be very careful, but I promise I'll upload this thing. So these are the area where all the less than conditions are filled up from the restrictions. Now, if you plug this value, you will get there 0, you will get there 14, you will get there 27, you will get there 33, you will get there 30. Okay? So you want to maximize this function, right? You want to maximize this function. So what will be the solution? What will be the x and y? 4 and 5, right? If you want to minimize, then everything 0, 0, right? So that's the magic. This is called the simplex method. Okay, this method is going to be used in quantile regression. Understand? So there is a subject known as the operation research, operation management. In the management department, operation research and manufacturing engineering, industrial engineering, those people, what they do, industrial engineering, manufacturing engineering, they mainly focus on this optimizations. There is a software, Cplex software, and then Python. Maybe I will show you one computations by using Python so that you will like it. Okay. So I have given you the background how the parameters of the quantile regression are computed. That is known as the linear programming. Let me start doing now derivations. Do you want to take a 5 minutes break? So it is 1 hour. So you can take just 5 minutes break, okay? Let me draw this. Let me take a photo of this. Then I will send it to you. And from next time when I compute, when I will show these things, I will show this in the graph paper. Okay. I took the picture. Let me check quickly one thing. So quantile regression and linear mixed effect model together will be one homework. So I will assign new homework next week, not this week. Okay, let me wait one more minute then. Okay, so let me write the equation. It can be shown that quantile theta is the solution to arg minimum with respect to xi 1 over t. So that means total number of observations. Here I will spend let me spend few moments in here. Have you seen how this equation has been written? So when this condition YT, as I said, 75th percentile means what? 25th percentile in the top, remaining 75% is in the bottom, right? So that means if I put here 75%, so get up there. So xi is the 75 percentile value which you want to compute. Xi is one of the 75% value of the YT. What is the meaning of this xi? Xi is the one of the 75%, like one value from YT, which is a 75th percentile. So when this exceeds that and this theta to the 75 percentile, so it is get up there. If it is less than, then this is a 25th percentile. That is the way they have formulated this value. So when quantile regression is fitted, so you will see in the homeworks in the real life example that I'm going to discuss, you will see line is fitted 85th percentile, bottom 85 percentile, lot of data points, and top 15 percentile, only few data points. That rationales come from here. So this xi is a 75th percentile value, this xi. So that means YT value greater than this. So that is why I put a 75th percentile. And this is 25th percentile. So in that case, it is less than that. So this was the problem existing. What these two gentlemen did, Bassett and Coenkar. In 1978, in a It was not an econometrics paper. It is Journal of American Statistical Association, JASA. 1978, what they did, they replaced this part by X beta. They replaced this part by X beta. So what is their equations? Their equation is this. Arc mean, and then they put here with respect to beta, and then the rest of the thing they put here yt greater equal to x beta prime, and then they put here theta yt So this is their formulations. If this could be done, then that could be done. Okay. So after plugging these things, then how do you write error? Y equal to x beta plus epsilon, right? Then you write epsilon equal to y minus x beta. You write this, right? So if you write this, then you can write this part equal to arc minimum beta. Now this part should be replaced by the greater equal to 0 theta epsilon t plus summation epsilon t less than 0. You can put here 1 minus theta because error is a combination of positive and negative values, right? Error we cannot get, but error we can estimate. In a production process, you cannot immediately get the error, but you can estimate. Okay? In a peanut production factory, you give sugar, you give oil, you give butter, you give peanut, altogether you give maybe 10 ton and then produce come up as a 9.5 ton. Understand? So some of those are system laws. So what we have done here, we plug these things in here. Okay? Error we can estimate. Now the equation reduces to that part. Now, if we put theta equal to half, we have a symmetric weighting of observations with the positive and negative residual. If theta is not equal to half, then the weighting is asymmetric. If theta equal to half, we have a symmetric weighting function. Of observations with positive and negative residual. If theta is not equal to half, the weighting is symmetric. Weighting is asymmetric. The weighting is asymmetric. So it could be further written in this format. So this one could be further written this one could be further written like this way. How? We can write it t goes to 1 theta I yt less equal to xi theta. Like, no, this is my error term. I should not mess up with this one. This is my error term, epsilon. This is the indicator function. If arrow term is in there, if this is less than that, then it will be just theta minus 1. Because on that part, if that will be negative, it will become theta minus 1. On the other hand, if it is greater than yt greater than xi theta, which is a quantile value, which is one of the value of this, like one of the values of that, if this is less than that, then what will happen if it is greater than that? Then it is 0. So 0 means theta times this, that one. This equation, it reduced to that equations from there, under that indicator function. This one will take value 1 or 0. If it is 0, then first part. If this is 1, then it is second part. This could be written like that way. So this could be now further written, since loss function is piecewise linear, since loss function is piecewise linear, solving it is a linear programming problem. Solving it is a linear programming problem. So replace absolute values by positivity constant. What does that mean? From here, I got this error positive. From here, I got this error negative. So positive and negative part can be written like that way. Which further be solved for beta and this is a negative one. This is a negative. So what is the condition now? Like the way linear programmings that we have written, in here, we have to put like this way. So that format would be in this one. From here, this is our main objective function, which we want to minimize under the what conditions? Under the condition is that y x beta plus this minus this, and then this should be greater than 0 and this should be greater than 0. So that means y minus x beta, that should lies between this and that. In some example for 3, 4, 5 data sets, linear book y has a series of data, right? And corresponding to x series of data, right? How many constraints? Lot of constraints, right? Those are the things you have to optimize. But for the 4, 5 equations, that could be done manually. But now 4, 5, 6, 7 data, all of those data will not work. You have to work with a lot of data. But this is the formulations. The way original linear programming simple things was formulated in here, exactly these formulations is coming in there. Now let me tell you, quantum regression has a lot of applications. As you will be a applied researcher, maybe some of you, few of you will go to the PhD or rest of you go to the industry. If they will ask you to do kind of predictive modeling from the data, and the data is given to you. What you can do, you can fit the quantum regression for the top 10%, top 25%. In addition to the normal regressions, you can also feed the quantum regressions. And suppose you work in the Amazon, then you can find if these are the people, they are in this week, they are the top 10% buyer. You understand? Because they spend maybe thousands of dollars. Okay. And then you can give a recommendation to your manager. Well, they spend thousands of dollars this month and previously this month, previously that month. We find some of this, the same pattern of this data. Their ID, though the ID is a fake ID, you would not be given their real ID. Their customer ID will be given maybe. Understand? And then you can give a recommendation to your manager. We should focus on this. We should give them some extra, like maybe what it called. If they buy one, then we can give them 25% off, something like that. Only reason quantum regression is difficult to understand because of the mathematics. Simple regression, what do you do? Just write the equation, first order derivative equal to 0, first equation, and then solve it, then you get the result, right? But the quantum regression is because of that theta, and because of two different parts, there is a one is top 15%, another is bottom 85%. You have to solve these things by simplex methods and other methods. Okay. So I'm going to discuss now some of the examples from the materials that I have uploaded in the D12. So let me go there. The solutions, and in this page, I also discuss something like this. Try to understand this, why theta -1 and how these values working. So this is coming from one of the handout that I have given. So how they compute the distance like this way, and are you seeing how they compute these things? This is in the top one, so tau d2, and this is the bottom one, 1 minus tau d1 and d2, and finally find this value. We got 0.53. Are you seeing how did I compute these things? So that's the way All of those things, this is just the only one. All of these things are computed and finally come up with the result. So I just have shown you only one thing. So let me take you to some of the materials that I want to discuss. In this case, see basic of quantile regression and let me take a look. Yeah. So these are the all Python codes has been written in there, and they feed a OLS regressions and 10%, 25%, 58%, and 75% and 98%. Okay. And then they have given some explanations how all of this has been explained. Okay. So in your report, when you write, read this one. This is just maybe 10 minutes to 7 minutes read to understand. And code is provided in here, which is a Python code. Understand, right? Okay. Here is another one. This is complete the R. This has been used the R. So data is showing up like that way. Data is showing up like this way. In that case, if you fit a average line, it will go like that way, right? But there is a spreading up something like that. This one is 95th percentile. Previously, this is the 90th percentile one. So here the codes and different values of tau. Tau equal to 10%, 28%, and 38, 48 percentile different percentage value are considered in here. And when this is the 10%, this is the intercept value, and this is the beta 1 value. This is the 98th percentile, this is the intercept, that is the slope. And they consider here many different lines. Just 2 lines of code. Are you seeing QS equal to 1 to 9 divided by 10 and RQ, regression quantile Y given X, data set that tau. So they will give you all the results very beautifully like this format. Okay. You have a data, you will run this and you can create some graph like that way. Clear, right? Very easy homework will be. This is the document, quantile regression code and explanation. This is the code. This is the code, okay? So this is already I uploaded in there. Anyone has question? So I recommend you thoroughly read these documents, okay? Getting started with the quantile regression. This document, if you read thoroughly, you will understand how quantile regression work and how code should be implemented to the data, to the problems that you are going to solve in your homework problem. So this is the document, okay? So then in this case, now where is the another one? No, not this one. I want to show you another thing. This is by using SAS. This is by using SAS. I want to show you, is this the hand derivation? No, this is not I want to show. This is what I already discussed. Quantile regression derivation. Quantile regression book. Derivation from medium. Let me check. Yes, I think there's one. Yeah. So this is some interesting discussions in here. I read this 21 page of document, but if you do not have a time to read all 21 page documents, start reading from the page 12 to all the way 21. Okay. This is the document. I want to show you something what they have done. Okay. They take they take 8 pairs of observations. 8 pairs of observations. Okay, they take 8 pairs of observations. So first pair, second pair, third pair, fourth, fifth, sixth, 7, 8. 8 pair of observations they have taken. Each has x1, y1, x2, y2, x3, y3, x4, y4, x5, y5, x6, y6, x7, y7, x8, y8. 8 pairs of observations. Then they consider 8, choose 2, which is equal to factorial 8, factorial 2, factorial 6, which could be written as 8, 7, 2 equal to 28. They constructed 28 lines. How? They consider 1, 2, 1 and 2, they consider one line. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. And then they consider 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. And then they consider 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, 4, 5, 4, 6, 4, 7, 4, 8. Then they consider 5, 6, 5, 7, 5, 8, 6, 7, 6, 8, 7, 8. So what they are doing in here, pair 1 and pair 2, they constructed a line. So they wanted to make these things very simple to the audiences. So they are considering that many lines in here. So there are altogether 28 lines. 28 lines they have computed in here. From these 28 lines, from this line maybe is coming from the pair 1 and pair 2. Pair 1 has a point, pair 2 has a point. So pair 1, pair 7 has a line. Pair 1 and pair 8 has a line. So altogether 28 of those lines they have constructed, and they are claiming that among these things, this one is the median line. Half of these lines fall, half of these points fall below this, and half of this falls above it. The dotted one is the median line. And corresponding to here, whatever X and Y in here. For example, if this is my data, I think I can write it in here. No, I cannot write it in here. Yes, I can write it in here. Each line has a slope and intercept, right? Each line has a slope and intercept. Slope is beta 1, intercept is beta 0, right? So from there, they have found beta 0 and beta 1, and they have plugged in there. Are you seeing? Are you understanding? And then they are finding a feasible solution in there. Are you seeing these things? This is the most easiest way to explain this complicated linear programming, because they purposely took just the 8 pairs of observations. Because if I take 100 pairs of observations, then if people understand for the 3 or 4 or 5 scenario, then it will be well said in their head, then they can think it for the large number of observations, right? What they have done, 8 pair of observations they have taken. First pair X and Y, second pair X and Y. These 2 pair has a line. They are creating one line. First pair and 7 pair. First pair means X and Y. First pair, X is in here, Y is in here. So they are putting X and Y. All of these lines they have found. From this line, so slope means what? How fast and how slow you can go, right? Slope means what? Your target is to reach 10th floor. For example, what is the pen? This is not the pen.
Yeah.
Okay. So take a look. Take a look. Suppose this is the target I want to go there, right? 10th floor. This is the 10th floor. 10th floor. So slope is what? How slow or how fast I can go, right? And this is the intercept, right? This is the beta 0. So from this line, I can get intercept, because this is the intercept. Okay, it is coming in there. This is the intercept, negative intercept, all of these things. So intercept value I can get. I can also get the slope value. So tangent value, that means slope value, can be computed. There is a formula for that, right? Right? So this beta 0 and beta 1, they have computed from there, and then they plug it in there. 28 lines, 28 beta zeros, 28 beta 1. So corresponding to 28 beta zeros, there will be 28 beta 1. They plug it in there, and then they find the feasible solutions in there. So from there, didn't I show you by showing the graph? From there, what value maximize the function? They are doing the same thing. So after doing these things, then they go to the further stage in order to convince the audiences that this calculation is actually giving. So when they have written these things in this format, they have a name in here. And then are you seeing how did they put these things? And then finally plug it in there. The purpose is to show a convex function. Okay. So convex functions mean it has a unique solution, something like that in the optimization problem. So they put a convex function, like if all of these things go like this, so it is like coming like that way. And finally they said that that's the way solutions could be obtained. It's called polyhedral surface and its projections. So the people are sitting there. If you do not do your work, and if you have some idea for research, if you do not do, someone else will do. Understand? Because they have to complete their PhD, right? So I have to complete my PhD and I have to do some works, right? But some other people did not do. So when you go to the school and universities, like the professors are sitting there, they are reading the research article. I'm reading the research article. If any student wants to come and work with me, well, then I'm giving, this is the problem, you can go and you can work on that. I know what problem is not solved and what applied problem you can do, which I can give, right? So if you do not do the work, someone will do the work, and someone just give the advice in 1975 and 1977, this quantile regression come into an existence. See, regressions was proposed 1805. Then this, all the regressions that I discussed, it was developed after 1970. So it took almost 170 years, right? Ridge regression 1970. Quantile regression 1977. Lasso 1996, 1995. And then elasticness 2005. Okay. So how many lot of years is gone? Why now people are saying that what university is teaching is getting more and more obsolete because the industry is in different level. Yes, because industry, you are facing the real life problem challenge. You understand? Take a look that Google is existing there, IBM is in there, Yahoo is in there, Microsoft is in there, but cloud business is done majority by them. They started way earlier, right? Yahoo, IBM, Google, they started way earlier. Why Amazon is the prime, is champion in cloud business? Because when Amazon started the business, they said a lot of people is clicking, a lot of people want to buy their ideas. So they are engineer and everyone think that, well, so down the road, everything will be in the cloud. Understand? So that is why they have started investing in there. And the Microsoft has the genius guy, the Nadella, Satya Nadella, right? His name is. He was very good, is overlooking the cloud business. And Bill Gates stepped down. They said that you should appoint him because he is the master. Because ultimately, everything will be in the cloud. Did you see the floppy drive, floppy disks? Floppy, like small floppy disks? And then definitely you have seen CD, DVD, right? And then definitely when in 2006 I came to the USA, everyone has a iPod. Music, everyone has a music iPod. Where it go? Now everyone has a phone. You still listen that thing, right? But whatever song you want to listen, just go to the YouTube, right? Day by day, nowadays things are getting obsolete very quickly. Very quickly. So believe me, like the airport that Apple brought, and they already made more than $15 billion of business. And my niece came to Bangladesh and she bought one airport by $170. I don't know about the quality, but 3 days ago I buy one from online, just $5. Just $5. You said Timu, right?
Yeah.
Who is this? You do the Timu business? Just $5. And then when I got it, my wife is saying, "Are you sure it is gonna work?" I said, "Let's try." Then I said, "Well, it is working. You wanna try?" "Oh, it's working." Then she said, $171 in 2019. Now it is just $5, right? Yes, everything changing very quickly. So if someone say that, well, what university is teaching is not that updated compared to the what market needs, because you are facing the new challenges, so that is why you're developing those things. You understand? We professor, we are developing new methods, new things. We cannot catch up with in certain cases with the industry. So down the road, once you come up with the idea, immediately implement it. There is many examples. See, Google is in there, Yahoo is in there, LinkedIn was in there, but Mark Zuckerberg went to the Harvard. One idea came, And he was exhausted days and nights. First, to create a website so that each and every students can share their profile, can share everything. Right? There are many talented students, right? And I have seen that those students who are focusing exclusively for the absolute GPA, because their head and mentality and everything going to the bed and waking up from the bed, how can I get 4 GPA? Read the book very rigorously. They are in here, they are getting maybe very good researcher and absolute GPA because they cannot think outside of the box. On the other hand, at the same time, they are not getting the problems. That problems they can solve and then they can get a solutions and become very successful. Understand? Take a look at that, the Airbnb. How the idea come? Take a look, like the Uber and the another one Lyft, right? You cannot believe how much lobbying happened in order to stop Uber and Lyft by the taxi cab companies. The senators and then everyone, they try to convince. Now taxi business is gone, right? Taxi business is gone. So now the things is changing very rapidly, and if you have only limited knowledge on some of these things, it is very difficult to survive now. Very difficult. You have to know a lot of things. You know one thing, and by the time it becomes obsolete, now you have to know another thing. Okay, can you believe if my grandfathers, they come up with a graveyard now, if they will say that we walk with like $1,000 phone every day, they cannot believe it. In 1980s, when I was in school, okay, if someone said that each and every person will walk in the road with a $1,000 devices, they would not believe it. Now it's nothing, right? Yeah. So all the regressions that I have discussed today, it was developed just in last 50 years, 1970, 1975, 1995, 2005, and these are the things. So next class, I will discuss a linear mixed effect model for the longitudinal data. Whatever we have discussed, it is for the cross-sectional data. So that means there is no repeated measurement. And next class, I will discuss longitudinal data and the linear mixed effect model, their derivations, and homework will be assigned, which will be the 7th week. And then 8th week, there will be exam, 30 to 40 questions, some basic questions. How does quantile regressions differ from the multiple linear regressions? What is the penalty used in the lasso regressions? How does it differ from there? What does sparsity means? Understand? And then when we use negative binomial regressions, okay? So these are the questions I'm going to ask you up until linear mixed effect model. So I know we have another 30 minutes. If you have questions related to homeworks or any other things, you can ask me. I cannot finish both the models together, so that is why. So, but I ask you read these things, page 14 to all in here, then you will understand how theory works. Understand? So if you will read these things, then you will understand how the theory works for the quantile regressions. And R and Python examples I have uploaded, read those things. And next week when I'll give you the homework will be easier for you to solve. Okay, let me see if someone send a message. Okay, thank you. So Eric and Vaishnavi, you have any questions? If you do not have a question, I'm going to stop in here.
Can you hear me?
That's it.
I have a question, as I'm not sharing screen. If we did the homework in Python, were we supposed to do an sklearn or stats model?
Yes. What is it is respondent BMI? Respondent. BMI means body mass index. Body mass index means height and weight, they mix these things, they compute a new measurement, which is better instead of using height and weight. If we did the homework for today in Python, is current fine or are you supposed to do? It's okay. Let me see. Check. Or are you supposed to use state model? Any package you can use, Eric. Okay? Yeah.
I have a question. For the RBMI, in the last semester, you gave us the data set and you gave us all of it. And the RBMI.
Responded body mass index.
No, respondent bet marriage economy and the data set.
Oh, part to marriage interval. Yeah. Yeah. It is a respondent part to marriage interval. So it's no. If I already write it there, then why did you ask me? No. That is just marriage first, but you put me in danger. Okay. Just a second, Eric. I don't think you need to standardize this data. You don't need to standardize the data. It is not a machine learning model. It is not a machine learning. I'm not doing any machine learning. You don't need to standardize or anything. Okay. You standardize the data? For which one?
For the lasso, the winch, and the dimension.
Do we need to do the standardization?
I mean, you don't have to go. It's not necessary. It's not necessary. Yeah, because when I didn't standardize, I was getting the same output. Like,
so you standardize the entire data with the all response and covariate?
yeah.
What's the response?
So if the variables are not of the same scale, I mean, it doesn't really do.
No, if variable are not in the same scale, those are the things we do clustering thing or maybe in classification thing.
Oh, it's not necessary in this.
No. Why do you? No.
Also, but does it matter if you already did that?
Okay, so what's the rationale for standardizing the data? We need to standardize the data for the classification and clustering. In that case, we are measuring the distance between two points, and one is in thousands scale, another one is like 10th scale. So in that case, classification. But here, why you are doing the standardization?
Does it affect the data? But Professor, if we don't split it, how will we measure the performance? Not standardization, but splitting the aspects.
So you are doing test and training?
Yeah, I tried to like which model is working right now. So see that, but then that.
So here I just want to take that multiple linear regression model and the Riggs model, how we are
I tried that, but then I removed it. It's just coefficient.
just coefficients, yeah, just coefficients. I want to see how the coefficients behave when we move multiple regression to Riggs and Riggs to lasso to elastic net. How the coefficients behave.
Yes, coefficients will be near to zero.
Yeah.
So will have more zeros
Yeah.
and elastic will have lesser number of zeros, but it will still have.
Yeah.
Does it matter if you can spot the difference in the models, like the coefficients, even though we do the splitting the test and train?
No splitting, no test or training.
Oh.
That is called the machine learning thing. Here I just give you.
I did increase the output. Like I don't. I use.
So, Professor, what if I don't that? You're supposed to manipulate.
No.
in one of those models, it penalizes to zero, like you have some of the variables completely equal to zero. Yeah, but that's still happening. Whether or not, depending on how you assume.
Professor,
Yeah.
What should
if I say use of data, can I still send it to them? Because I'm using a laptop.
Okay.
But also, what's collaborating standardized? It's not just for the-
I told you don't do the standardization. I want to check. Don't do the standardization. And I did not mention. I did not mention.
end of doing something that's like a kind of
No, the homeworks that I mentioned, I never mentioned anything like standardization in the entire homework. I just clearly mentioned, I want to see how the coefficients behave.
So I do understand the purpose of the assignment. Understand how the coefficient behave, right? And talk about their difference.
Yeah.
Now, standardizing across different explain them, doesn't matter.
Splitting we usually do for training the model and then testing. How our data perform, how our model doing. Right, so here we are not doing any machine learning thing. We are just checking how these four models work when we run this on a specific set of variables, and how the parameter got shrunk, and how parameters are kicked out, like the variables are kicked out.
That really happens.
Yeah.
That happens my coefficient.
Yeah.
Do I standardize? Do I did that? I just use the train data. That's it. It's not like I went all the way to machine learning. No. I
It
just
was just a line of code, like, it was
yeah.
just, like,
But
after
the
you
thing is that I still have my coefficient behavior.
Yeah, exactly. We have done it that way. We still have those coefficients.
You will still have them behaving that way.
like that, giving the output you mentioned.
Okay.
So can we still leave it like that?
And explain it
And
very well.
explain it very well.
Okay, report it in the explaining the
Thank
report.
you. Thank you, Professor.
Mhm.